Let's work through some more two-dimensional problems. I'm going to have you watch a clip. This is from the end of Big Buck Bunny. Let's see, I'll have it start at the appropriate time. Well, you're going to watch at the end of Big Buck Bunny. Remember we watched the free fall clip where the squirrel, this flying squirrel, fell onto these limbs that have been sharpened, and the bunny, Big Buck Bunny, exacts his revenge. And so we're going to pick up there. That's at 7 minutes and 30 seconds. You just watch about 30 seconds or so of that clip, and we'll see that Big Buck Bunny that the squirrel is actually suspended up in the air. And I want you to think about the forces that are involved in this. Think about the forces, and then we'll draw a force vector diagram outlining all those forces. We'll make some estimates about some of the values, and then figure out what is the force actually keeping them up in the air. So why don't you go and watch the clip? Watch it right here. All right, so in this clip, we had a couple of things. So we had our squirrel here. They had several forces acting on them. We had, of course, the weight, Fw, and then we had the force due to the string. I'll call that Fs. And then we also had the force due to the wind, and I'll call that what do I call it down here? Well, I'll call it Fa for like the air resistance. Now, I want to make some estimates about that, and I want to figure out what is the force due to the air resistance. All right, now, first of all, I want to estimate what is the tension in the string. That's this Fs that I've called it, or I can call it Ft if you like. So, a string, maybe a few pounds or so when you're flying a kite, a few pounds. And a few pounds would be, since a newton is a quarter pound, then a few pounds is about 12 newtons, or I'll call it 10 newtons. I need to estimate the weight, mass of a squirrel. A big squirrel is about a kilogram or so, it's a couple pounds. So 1 kilogram times the acceleration due to gravity, which I'll just round off to 10 meters per second squared. All right, so that's equal to 10 newtons. So I have 10 newtons for both the weight and for the tension in the string. I'm going to draw my vectors here, my coordinate system. There's my x-axis. There's my y-axis. I want to know what is this angle. I'll call it theta. And then I also want to know what is the magnitude of that force Fa. I'm going to estimate what this angle is. I'll just say it's 45 degrees, just to make it simpler. And it's pretty close, 45 degrees, it looks like. Now, I have 3 force vectors. I know that this is a static situation. That means that the acceleration is 0. And further, it means that the sum of all the forces equals 0. So I can say then that Fa plus Fw plus Fs these all equal 0. The vector sum of those is equal to 0. So then I can say that Fa has to equal the exact opposite of the sum Fw plus Fs. So if I want to find the vector Fa, that is the force of the air resistance that's pushing on this squirrel, then I just need to do the vector sum of Fw and Fs. And this goes back to what we did in chapter, what was that, 3, where we added vectors. So first I want to find the x component of the weight. Now notice the weight is only in the y direction, so the x component is 0, and the y component is 10 newtons. It's actually negative 10 newtons because it's in the negative direction. And now I want to resolve my Fs, that's the tension in the string, into its x and y components. The x component is going to be 10 cosine of 45. Notice this is positive because the x component, if I look up here, the x component of this force vector goes in that direction. The y component is going to go in that direction. So the y component then is going to be negative 10 sine of 45. Now this is equal to negative 7. This is equal to positive 7. So if I want to find the x and y components of Fw plus Fs, just as I did in the previous, in chapter 3, I just say 0 plus 7, add up the x components, equals 7. Negative 10 plus negative 7 is negative 17. All right, so if I want to know the x and y components of Fa, which is equal to the exact opposite, well, what do? I just take the exact opposite. I say negative 7 and positive 17. So now my vector Fa looks like this. It has an x component that has a value of negative 7, and a y component that has a value of plus 17. So that means that my vector FA looks like this. I can find this angle theta, and I can find the magnitude. The magnitude of FA equals the square root of 17 squared plus 7 squared, or negative 7 squared if you like, but the negative goes away. And that's equal to, let's see, I think it's 18. Yeah, 18 newtons. And then I can also find this angle theta, just like we did in chapter 3. Theta is the inverse tan of the y component over the x component. That's 17 over 7. And if I calculate that, I get 67 degrees above the negative x-axis. Being very clear that I get my direction appropriately labeled. And that's the answer, 18 newtons at 67 degrees above the negative x-axis.